Well, so I begin. Last time we discussed a construction, very important construction in differential topology analysis, which assigns to every manifold a sequence of spaces of differential forms of different degrees. So M is an n-dimensional manifold. And there are spaces, omega q M. This is the space of exterior forms, differential forms. Of degree q. What we know about them? First, so q here, first of all, is between 0 and n. If q is greater than n, I will use this notation for just 0. Then omega 0 M is the same as the space of functions. See infinity functions still. I never consider other functions. And also we have local presentation a form alpha from omega qm locally I mean within the domain of local coordinates, has the form the sum q, and this is a function I write of x, meaning x1, xn local coordinates on a manifold times dxi1 dxiq. Here dx within the frame of this theory, dx is the differential of the function x dxi, or the function xi. Xi is a function which is defined within the domain of local coordinates. Functions have differentials, which are forms of degree 1. Also, it should be mentioned that two things I want to mention. First, that there is a multiplication. So if alpha is an omega qm and beta is an omega rm, then there arises their exterior product. Of degree q plus r, which has very direct algebraic properties, and in particular, alpha wedge beta is equal to -1 to the power qr beta wedge alpha. Also, the associativity holds the multiplication with the form of degree 0 of this function is the usual multiplication by a function, and so on. And then, if there is a smooth map of one manifold into another manifold, arbitrary dimensions, different dimensions in general, then there arises for every q the map between differential forms in the opposite direction. This map basically is determined is induced by the differential of f, which maps tangent vectors to m into tangent vectors to n. This is more or less the usual general theory, plus one more description which we consider for differential forms. Namely, if x1, xq are absolutely arbitrary vector fields on M, then for a form alpha, there arises a function. We unplug all these vector fields into alpha, C infinity M, and alpha becomes this operation, sort of multilinear form on the space of vector fields with values in functions. And when I say multilinear, I mean linearity over functions. That is, if alpha depends on q arguments, if you multiply any of these arguments by a function, then the value will be multiplied by the same function. This last description can be considered as actually a version of definition, alternative definition of differential forms. We can define them like this. It is sometimes convenient, sometimes it's convenient. The convenience is that we have a description of differential forms in terms of coordinates, but this description, this definition, is coordinate free, which certainly in certain cases can be used in the usual way for proving different results, if not for computations. Now, our next goal, and it was formulated in the end of the last lecture, is to describe one more operation, which actually is. You can notice that when I introduce an operation, I always say that it is the most important. Somehow it is true. Every operation here is the most important. One more most important operation. It is differential. Again, for a very arbitrary manifold, M, we have a map D of omega qm into omega q plus 1m, which is defined for every q. The following three properties may be regarded as axioms because they actually determine the operation. First, if q is 0, then D becomes the map of the space of function into one forms, and this is the usual differential. Differential which is considered in calculus. Two more properties. The second one is the product rule. If alpha is in omega qm and beta is in omega rm, this is d alpha wedge beta plus minus 1 to the power q, this q, alpha wedge d beta. And the property number 3, one more most important property, that applied twice, it is 0. That is, the differential of an arbitrary form is 0. I say this and I claim that actually this construction belongs to multivariable calculus and is considered there. Although normally teachers in multivariable calculus, and I have a modest experience of this myself, never mention that d squared is 0. This is sort of maybe too misleading for the undergraduate students. For you, it should be not misleading, especially for those of you who have some knowledge of topology where this is a very common property. My claim is that these three properties uniquely determine the operation D. And there are two ways to show this. And I want to say first that the uniqueness, even before we know that this operation exists, the uniqueness is actually almost obvious. Let us look at this using the coordinate presentation which we have. So suppose that locally alpha is the some function is a function in the domain of local coordinates actually, since my differential should be linear with respect, it is a linear map of the vector space omega q m into the vector space omega q plus 1m over numbers, not over number functions. It takes sums into sums, and so we can consider the case when alpha is one-summand, just for some function f times dxi1 dxiq. Then, if we believe in our axioms, actually in all the three of them, then what is d alpha? From our axioms, from the axioms. D alpha. Product rule. A certain product rule is formulated for the product of two factors, but actually can be applied to the product of any amount of factors because the product is associative. So we need to take this D and apply it to F. Don't forget F. This is to everything. The first summand will be df times, now I use this wedge because it's not a function anymore, dxi1 dxiq. Now we need to apply d to this, but this is 0 because dd is 0. And all actually the rest of the factors, q factors, none of them makes any contribution into the final result because dd is 0. So this is the formula. And since we know what df is, we can conclude that at the very least, my axioms determine the differential uniquely. Because we can compute the differential of an arbitrary locally given form, but it is a local operation. Yes. Let us look at this formula, because I want again to say that it is not totally unfamiliar to you. df. So now what I'm doing now is not actually an immediate part of the proof, although I will be using that. So df, as we know only too well, is the sum over of j. df over dxj times, I can write times dxj, right? It is the usual formula for the differential, and actually we know this formula. Then we need to take this and multiply by all this. But the product of dx's, of differential forms of degree 1, is anticommutative. So if actually we take this sum, multiply by this, and j is among one of those numbers i1, iq, it will be 0. it may be not important, but still, the sum j doesn't belong to I1 IQ. And here I write df over dxj, dxj, dx I1, dx IQ. This expression, you may find it not satisfactory because in my, yes, no, it wasn't written here, but I had this in mind. I1 IQ formed an increasing sequence. If I write like this, then j is not necessarily less than I1. So to make this this formula more having more usual appearance, we need to take this dxj and to move it to the appropriate place to make the sequence increasing, which certainly will result in the certain amount of minus 1 to some power. Now again, not for proving any theorem, but simply so suppose that we have a function of two variables, f of xy. Then what is df? This we know, df over dx, dx plus df over dy, dy. But what if we have a form of degree 1? Here p and q are functions in x and y. And what is the alpha? Well, I prefer to write it without first any omissions. It is dp times dx plus dq over dx, dx plus dq over dy, dy, dy. Now look at this expression. 4 terms, but 2 of them disappear immediately with dx times dx here and dy times dy here. No. The 2 remaining terms contain dx times dy times dx and dx times dy. It is very reasonable to switch in the first case dx and dy, and we will have a formula. Please don't say that you have never seen it. dq over dx minus dp over dy, dx, dy. This is the differential of this form. Certainly I can continue, but first of all, certainly this expression dx, dq over dx minus dp over dy is not totally unfamiliar to you because it is a part of many theorems in multivariable calculus. If nothing else, of the green formula, this is one thing. Another thing, that there are many other, I just make this computation for the form of degree 1 of 2 variables, but I can take 3 variables. I can only add that if you consider a form of degree 2 in 2 variables, then its differential should belong to omega 3, and no omega 3 for the plane. It is 0. So for every 2 form, the differential will be 0. This is for 2 variables, but actually a similar fact holds for any manifold with dimension n. The differential form of degree n will be 0, simply because there are no forms to degree n plus 1. If now, we have some work to do. Uniqueness, yes, uniqueness is uniqueness. But also we need to prove existence. How to prove existence? Actually, since we have a formula, then visibly, but not actually, visibly this formula gives you the existence. This is the formula which describes the differential, say that one. But two things. First, it does depend on coordinates. So if we make a coordinate change, actually x1, xn are coordinates in Rn or local coordinates on the manifold. Domains of local coordinates may overlap. So it is possible to imagine that at around some point there are two coordinate systems, x1, xn and y1, yn. And then the functions y and x can be expressed as functions of each other. Coordinates, if we have two coordinate systems, then coordinate functions from one system are functions of coordinate functions of the other system and vice versa. We need to check that when we take another coordinate system, take the same form and apply differential defined by this formula to that form, then actually we will get the same result. And this, I will not do this, but you understand that if we have a form like this, the sum alpha I1 IP dx of x dx I1 dx IP, the sum over i's. Then, if you have another coordinate system, then certainly we can express first of all differential. So x's are functions of y's are functions of x's. So I can write, let's say dxj, ds dxj, let me write dxi, is equal to the sum dxi over dyj times dyj, right? If I replace every d differential here by this expression, I will have dy's. Here also, I need to replace x by y. The same form I will have its expressions in y coordinates, and I can consider the differential using that formula. Also, you see that this differential involves derivatives with respect to x. If I want to have derivative with respect to y, then I have to use your beloved chain rule. After I do all this, I will get a certain expression which involves a lot of partial derivatives. And then pure algebraic computations, which I will not do here simply because it is too boring, but very direct, show that actually, yes, when we this expression is invariant with respect to coordinate changes. So if we consider the differential of the same form with respect to a different coordinate system, then actually the result will be the same. This is one thing. Another thing is when we consider differentials. Yes, it is very interesting that we are able to define the separation D using local coordinates, but we need to check. The axioms, because we used the axioms, but only partially. Right? And in particular, we used everything, but every axiom we used only a tiny part of it. So we need to check that the differential, which is defined by this formula, and now I can consider local coordinates as given, fixed. The differential, which is defined by this formula, satisfies the three axioms of ours. Number one is direct. differential from omega 0 to omega 1 is the usual differential for functions simply by our construction. So if we have no this dx1, dxi1, dxiq, then simply differential above becomes differential above in the usual sense. So the axiom number 1 does not cause any difficulty. Now number 2. We consider now two forms, alpha and beta. Let me write it. Alpha is f dxi1 dxiq. Beta is g dxj1 dxjr. Now I want to find alpha wedge beta. I multiply this by this. Well, g will stay here, but it commutes. Having degree 0, it commutes with differentials. So the result will be simply fg dxi1 dxiq dxj1 dxjr. And here I prefer not to pay any attention to the fact that actually there might be zero summands. It may be 0, simply if the set of i's and j's have a common number. And sort of the order is not right. We can switch the order, we can do everything, but this expression makes sense anyhow. Now 3 things. D alpha beta. Very much bounded by our construction. This is d fg times all these differentials, right? Now, d alpha is df d alpha wedge beta. Well, we will df times g and times all our differentials, right? D beta is this. It is dg dx j1 dx j r. And the last thing, actually I have no space for anything else, alpha wedge d beta dx f dx I1 dx jr, and then this wedge d beta dg dx j1 and so on. It is I. It is iq, right? This expression is okay, but I prefer to take this and bring it here. Why? Simply, well, I want to do this. Simply to have all the other differentials from the left to the right in the same order as here and here. This switch, q times, I switch a form of degree 1 with forms of degree 1. 1 is odd if you don't know. So every switch will result in a minus, and this will give you negative 1 to the power q. And this actually gives you all. Just look at this. Certainly, dfg is df times g plus f times dg. This is the common usual formula from calculus, and it's very, very obvious in any way. And here, when you look at these formulas for this, this, and this is a d alpha beta, which should be wedge here, which involves this, is equal to d alpha wedge beta, which involves this. And here, this sign should be neutralized. I neutralize it by multiplying by one more negative 1 to the power q. And I have my favorite formula. This is now on the board. You see how the axiom number, I don't remember what, number 2, can be checked. Okay? And the last part of this all, that dd is 0, is at least shorter than this. At least shorter than this. It is by the length between the previous two axioms. Number 1 actually had empty proof. Number 3 has this more or less short proof. And number 3 will have a very short proof. Look. Again, we want to prove that dd is 0. So I take a form alpha, which is f times I1 dx iq. I can write wedge here, but it's very strange to write wedge between a function and a form. Otherwise, it's also a wedge. Then I take d alpha. This is the sum j naught in I1 iq df over dxj dxj dx I1 dx iq. And I applied the differential to each one more, d alpha. And this will be what? I need to take one more number, say k, which is not among I1 and q, also not equal to j. And I will have the sum so jk is j is not equal to k, does not intersect with this set, and this will be df dxj dxk dxk dxj, and then everything else, dxj1 and so on. Now it's very obvious that this summand, more or less this summand, appears twice, because j and k can be taken in any order. If you take first k and then j, you have the same partial derivative, because second partial derivative is the second partial derivative. Second partial derivatives do not depend for infinity functions on the order. And then these two dxk, dxj in one case, and dxj, dxk in the second case. These two things cancel each other, because one is equal to negative the other one, which shows that dd is 0. So this is how the whole construction holds. So we have this differential. And I want to mention very briefly, but it is given in all details in my notes. I expect some comment from you, Henry, but probably if you want, we can discuss it after the lecture. You see, after all, differential forms are defined without any participation of coordinates. You remember what the differential form is. Not this expression f times dx1. It is a multilinear function, multilinear over functions, depending on q vector fields, q symmetric, with values in functions. The differential of a form, again, is a similar thing, only it has degree q plus 1, so it will be a q plus 1 linear form, depending on q plus 1 vector fields. And it's difficult to believe that there doesn't exist any direct way how to describe this differential right in terms of vector fields. And this thing exists. It is called Cartan formula. And actually, this formula, long after, many years after Cartan first invented, that probably was in something like 20th of the 20th century. It actually found its way into homological algebra, and it is used there. But here we're not speaking of homological algebra. I will teach homological algebra in the spring quarter. Now this formula. Suppose that alpha is omega q m, is an omega q m. So alpha is a function depending on q vector fields. Now d alpha depends on q plus 1 vector fields. And it is determined in terms of alpha by the following formula. To write this formula, first let us think a little bit. If we have, actually we have at our disposition a function of q vector fields. And now we need to create a function of q plus 1 vector fields. How to do that? So we need to take these q plus 1 vector fields and somehow make it a set of q vector fields. There are two obvious ways to do that. First, maybe too obvious to be used immediately, is just to drop one. It will be q. Second, take two of them and create of them one vector fields taking their commutator. We will be using both, and the formula is the sum s1 to q plus 1, negative 1 to the power s, all negative ones, unnecessary if we really want that the result would be symmetric. I take alpha, I apply it to this q plus 1 vector fields with x1 dropped, but it should be linear with vector xs also, so it should be, xs should be somewhere here, and this is about the right place for it. This is a function. We can apply xs to it. Then plus the sum negative 1 to t plus u. I take alpha. I first write the commutator of the two vector fields. And take all the rest, certainly dropping the two which I have already used. And this is the formula. And this is the formula. If q is not big enough, it is small, then this formula becomes actually very short and instructive. If q is, say, 3 or 4, we have many sums, especially the second sum, two arbitrary numbers between 1 and q plus 1. So q plus 1 chooses two possibilities. Also the signs and so on. And then this formula does not require any checking that it is well defined. It is well defined. Certainly the fact that it is symmetric is so simple that I will not even mention it. But we need to check the three axioms. Again, the axiom number 1 for functions is just by definition. This is not a problem. But the other two axioms both require verification, and this verification involves some dealing with these sums. So it may be sort of long, and in my notes As far as I remember, it takes approximately 2 pages to do this. But still, it is true. So this formula can be used as an alternative definition, as an construction of the differential. But now this is all. We have this differential. We know how it actually works with respect to multiplication. So the product rule. D squared is 0. Also, I want to mention, it is very obvious from any definition that this operation is what algebraists say natural. I mean that if you have an arbitrary map, smooth map, f of m into n, then I have what? I have omega q m, I have omega q n, I have omega q plus 1 m, I have omega q plus 1 n. Here I have differentials, and here I have, no, this direction, the map f star. And as algebraists say, this diagram is commutative. As ordinary people say, the operators d and f star commute with each other, can be applied to a differential form in any order. I will not check it, but it is certainly true. Now, let us discuss a very exciting thing. Some of you know that the equality d squared is zero gives rise to certain consequences, algebraic consequences. And now we will be discussing precisely these algebraic consequences. The theory of differential forms is very classical, terminology is classical, and as I often say to different courses, that it is pointless to try to understand the origin of the terminology, because terminology was created years and years and decades and sometimes centuries ago, when actually the intuition of mathematicians was very much different. And now we can understand the definitions which they created. Theorems, proofs, everything. But why these things, such and such things, are called in such way, especially in algebra, but not only in algebra. Sometimes it is pointless to discuss this. So just look. A form alpha, omega q m, is called closed if the alpha is 0. A form alpha is called exact if alpha is equal to d beta for some beta in omega q minus 1 in m. Closed forms as well as exact forms form subspaces of omega q m, but I want to say that the fact that dd is 0 implies immediately that every exact form is closed. Since d of d beta is 0, right? So we have the following spaces. Omega q exact is a part of omega q closed. This is a part of omega q m. All these spaces actually usually are infinite dimensional, always, if you don't count the case of zero-dimensional manifolds. Infinite dimensionals, but they're vector spaces. This inclusion actually gives us a possibility to take the quotient. This quotient space is called the qth de Rham's cohomology of M, de Rham. A miracle here. I call it a miracle. You see, these spaces are huge, omega qm. Huge space. Closed and exact, also huge spaces. But the quotient is small. In particular, for any finite dimensional manifold, it's finite dimensional. For any compact manifold, it's finite dimensional. So this construction, in some sense, in the sense of theory of cohomology, is very reasonable. It gives you a finite dimensional space which in general is not zero. I have 2 minutes actually left. Well, I gave 1 minute at the beginning, so 3 minutes left. Let us consider some simple example. M is R, just a straight line. So there are zero forms, just functions on the line, as in very beginning of calculus. A differential form of, so f of x is an element of omega 0. Omega 1, one form, g of x dx. Everybody knows it. How does the differential act? Everybody knows. The differential of f is f prime dx, right? So there are forms of degree 0 and 1, closed forms, very much closed. df is 0. Is it possible at all? If yes, then when? Have you ever heard of functions whose differential is 0? Yes. What are they? Wonderful, constants. So closed forms are constants, and the dimension of closed forms is 1 of this space. Exact forms, no exact forms, because no forms of degree -1. So H0 has dimension 1. Now, dimension 2, degree 1, f g of x dx is always closed, because the differential should be a form of degree 2 and no form of degree 2. When does the form h of x dx exact? Funny question. You have a function h. Is it a derivative of some other function? Henry, just think that you are in a calculus room, and I am a Math 16 student, and ask you, listen, Henry, if you have a function, is it a derivative of some other function? Then certainly in the calculus, immediately yes, take its integral. So every one form is closed, every one form is exact, and hence the cohomology, the quotient is 0. This is the very first example, but there are other examples. For my last words today. For people who know some topology, I can say that the Rham cohomology is related to the usual cohomology in a very direct way. This is the same. Thank you. Now I wish you all a very good nice holiday, and see you Monday.